All right, let's dive deep, shall we, into the world of tidewater glaciers. You know, those massive rivers of ice that flow right into the ocean. We all know rising sea levels are a big deal, and these glaciers are key players in that. So today we're going deep into a 2024 research paper. It's from the Journal of Engineering Mathematics. And we're going to unpack the science behind how these glaciers break apart. You know that dramatic process called iceberg calving?
Yeah, this paper, it doesn't just, describe the process. It actually digs into the math behind it, using what's called the Galerkin least finite element method to model how and why these glaciers break apart.
Okay, now I know that sounds intimidatingly complex, but stick with us. The researchers basically used this method to create a virtual glacier, breaking it down into smaller, more manageable pieces. It's kind of like analyzing a river's flow by studying its individual currents. You know, and they could then see how different factors influence the breaking points, things like water pressure and the shape of the glacier.
Right, exactly. And they specifically looked at three types of tidewater glaciers in their models. One that's lightly grounded, barely touching the bedrock, then one with a notch, like a bite taken out of it, and then one with a notch and what are called basal crevasses.
Basal crevasses. Okay, so those are the cracks at the bottom of the glacier, right? I'm already intrigued. What causes these crevasses to form down there, and how do they influence iceberg calving?
Well, think of it as like a tug of war between the immense weight of the glacier pushing down and the water pressure pushing up. And that's what the researchers call effective principal stress, or EPS. Kind of like when you squeeze a tube of toothpaste. The pressure combines the force you apply and the toothpaste resistance inside. And it's this stress that can cause cracks to form.
Okay, so the shape of the glacier, particularly the presence of notches, really matters.
Absolutely. The steeper the slope of the glacier, the more weight is pressing down near the ocean. And deeper notches and steeper slopes lead to higher stress at the base, which makes the ice more likely to crack and eventually break off.
Okay, that makes sense. What about those basal crevasses? Where do they fit into this picture?
Think of basal crevasses as like weak points in the glacier. The water pressure can actually force those crevasses to open wider, almost like it's wedging itself in there, exploiting any weakness it can find.
So water pressure is more than just a steady force. It can actively change the glacier structure.
Yeah, it is. And here's where things get even more interesting. The point where the glacier is grounded to the bedrock, it's called the grounding line. And that can actually shift due to factors like melting. And as the grounding line changes, so do the stress patterns throughout the glacier.
Wait, so even a slight shift in where the glacier touches the bedrock can have like a ripple effect on the entire system? It's like a domino effect?
Yeah, precisely. And that ripple effect can make those basal crevasses more likely to form and grow, ultimately leading to iceberg calving.
Okay, so we've got the weight of the glacier, the shape of the glacier, the water pressure, and the location of the grounding line, all contributing to the likelihood of a glacier breaking apart. It's a lot more complex than I initially thought.
Yeah, it is. And the researchers were able to simulate this complex interplay of factors using that Galerkin least squares method.
Right, let's talk about that method. I'm still a bit fuzzy on how it actually works. Can you break it down for us?
Imagine you're trying to understand how a complex machine works. You wouldn't just look at the whole thing at once. You'd break it down into its individual components, study how they interact with each other. And that's essentially what the Galerkin least squares method, or GLS for short, does for glaciers.
So instead of looking at the entire glacier as one solid block, they're breaking it down into smaller pieces.
Exactly. They divide the glacier into those what are called finite elements and analyze each section, taking into account factors like ice flow, water pressure, and bedrock friction. Then they use sophisticated equations to see how these individual sections interact, ultimately creating a simulation of the entire glacier.
So they're essentially building a virtual glacier inside a computer.
Yeah, it is. And this approach allowed them to capture the dynamic nature of the ice flow. You remember Glenn's flow law, right? Ice flow is like a very thick fluid. But the rate of flow can vary based on temperature and stress.
Right, so warmer ice would flow more easily, potentially making it more susceptible to calving.
Exactly. And that's why understanding Glenn's flow law is so important for this research. It helps explain why a glacier might behave differently under various conditions. The GLS method is powerful because it can take this nonlinear behavior into account, making the simulations much more accurate.
So they're not just looking at the glacier's shape and the forces acting upon it, they're also considering how the ice itself behaves under pressure.
Precisely. And by incorporating all these factors, the researchers were able to gain some fascinating insights into the mechanics of iceberg calving.
Okay, so let's dive into some of those insights. What did they discover about the relationship between these different factors, and the likelihood of a glacier breaking apart.
Well, one of the key findings was that the presence of those basal crevasses, those cracks at the bottom of the glacier, they significantly alter the stress distribution within the ice. They act like weak points, concentrating the stress in certain areas.
So even a small crack can have a big impact on the overall stability of the glacier.
Yeah, it can. And as the grounding line shifts, often due to melting caused by warmer ocean temperatures, the water pressure at the base of the glacier can actually force those crevasses to open even wider.
So the water is basically exploiting any existing weaknesses in the ice, driving those cracks deeper and making the glacier more vulnerable.
Exactly. And that's why understanding the interplay between water pressure grounding line shifts and basal crevasses is so crucial for predicting calving events.
This is all incredibly fascinating. But I'm curious, was there anything that surprised the researchers? Any unexpected findings?
One interesting finding was that when a glacier has a notch, the grounding line actually shifts further inland.
Wait, so having a notch carved into the glacier can actually cause the point where it's attached to the bedrock to move. I would have thought it would be the opposite.
It is a bit counterintuitive, but remember, we're dealing with a complex system with lots of interacting variables. The shift in the grounding line, in turn, affects the stress distribution throughout the glacier, making it more susceptible to calving in other areas.
So it's not just about the notch itself, it's about the chain reaction it triggers within the glacier.
Exactly, and this highlights the importance of understanding these interconnected processes if we want to accurately predict future calving events.
Okay, so we've talked about the shape of the glacier, the water pressure, the grounding line, and the behavior of the ice itself. Is there anything else we need to consider to fully grasp this whole iceberg calving phenomena?
Yeah, there's one more piece of the puzzle that's crucial to understand. The role of friction between the glacier and the underlying bedrock.
Friction, you mean like how easily the glacier can slide over the bedrock?
Precisely. The researchers in this study paid close attention to how friction between the glacier and the underlying bedrock affects the ice flow. They considered different types of bedrock and how rough or smooth they are.
So a rougher bedrock would create more friction, making it harder for the glacier to flow.
Exactly. And that increased friction can actually have a stabilizing effect, slowing down the glacier's movement and potentially making calving less likely.
Wow, so it's not just about the forces pushing the glacier towards the ocean, it's also about the forces holding it back.
That's right. And this is where the concept of what's called slip length comes in. It's a measure of how easily the glacier can slide over the bedrock.
So a longer slip length would mean less friction, allowing the glacier to move more freely.
Exactly. And the researchers found that even small changes in slip length can significantly affect the stress distribution within the glacier and the likelihood of calving.
So we have yet another layer of complexity to consider. The type of bedrock beneath the glacier can actually influence how it behaves.
Precisely. And this research highlights the importance of considering all these factors. The shape of the glacier, the water pressure, the grounding line, the behavior of the ice, and the friction between the glacier and the bedrock. To fully understand and predict iceberg calving events,
It's like a delicate balancing act, with all these forces pushing and pulling, influencing whether the glacier holds together or breaks apart.
that's a great way to put it. And this research is giving us valuable tools to understand that balancing act and how it might shift in the future.
This is a lot to take in, but it's fascinating to see how scientists are unraveling these complex processes.
Yeah, it is. And this research has some interesting implications for our understanding of climate change. Would you like to explore those?
Absolutely. I'm curious to hear how these findings might help us predict the future of tidewater glaciers and their impact on rising sea levels.
Great. Well, one of the things the researchers did was use their model to explore how changes in certain environmental factors might influence the calving process. For example, they looked at what would happen if ocean temperatures increased, leading to more melting at the base of the glacier. So they're basically running simulations to see how these glaciers might react in a warmer world, which is, pretty crucial given all the concerns about climate change these days.
Exactly. Warmer water, more melting faster, calving higher sea levels. It's a chain reaction with some pretty serious consequences.
Yeah, that's the general trend. But it's important to remember that each glacier is unique and will react to these changes in its own way, depending on its characteristics and location. It's not a one-size-fits-all situation.
Okay, that makes sense. It's like every glacier has its own personality and history. But even with those variations, the overall trend seems pretty clear. Warmer oceans mean more vulnerable glaciers. Did the researchers make any specific predictions about how much calving might increase?
Well, they explored, different scenarios, and it's complex to give, exact numbers, but their models showed a clear link between rising ocean temperatures and increased calving rates, which really underscores the urgency of addressing climate change.
Absolutely. This research is giving us a much clearer picture of the potential consequences of inaction. It's not just about saving glaciers, it's about understanding the intricate ways our planet is responding to the changes we're causing.
Precisely. And this study goes beyond just sounding the alarm. It arms us with knowledge and tools to understand the delicate balance of these systems and make informed decisions about how to protect them.
I'm curious, though. The researchers used a two-dimensional model for their simulations. Wouldn't a three-dimensional model provide a more accurate representation of real-world glaciers?
You're right, a 3D model would certainly add another layer of complexity and potentially reveal even more nuances in the ice flow and calving process.
So are the findings from this 2D model reliable? Should we take them with a grain of salt?
Well, the researchers acknowledge this limitation, and they suggest that future studies incorporate 3D modeling. But even with this simplification, the 2D model offers valuable insights into the fundamental mechanics of calving. It lays a strong foundation for future research.
That makes sense. It's like creating a detailed blueprint before constructing the entire building. Are there any other areas where this research could be expanded or refined?
Absolutely. One area that I find particularly intriguing is the role of meltwater in the calving process. We know warmer ocean temperatures lead to increased melting at the base of these glaciers, but how exactly does that meltwater interact with those basal crevasses?
That's a great question. Does it act like a lubricant, making the glacier more likely to slide and calve? Or could it potentially create additional stresses within the ice, contributing to fracture and calving?
Those are some of the questions that scientists are actively investigating right now. Understanding this meltwater dynamic could be crucial in refining our predictions about how glaciers will respond to climate change.
It seems like the more we learn about Tidewater glaciers, the more questions we uncover.
Exactly. And that's what makes this field so fascinating. There's a constant drive to understand these processes and their interconnectedness within the broader Earth system.
Okay, so we've discussed the research findings, the modeling techniques, and the potential limitations. But before we wrap up, I want to take a step back and talk about the bigger picture. What does this research tell us about the importance of tidewater glaciers in the context of climate change?
This study reinforces that tidewater glaciers are not just icy landscapes, in some far-off corner of the world. They are dynamic entities, playing a vital role in regulating sea levels and influencing global climate patterns.
So their health is directly linked to our own, even for those of us who live far from these icy giants.
Absolutely. The meltwater from these glaciers contributes to global sea level rise, which has far-reaching consequences for coastal communities worldwide. Understanding the factors that influence their behavior is crucial for predicting and mitigating the impacts of climate change.
This research paints a pretty clear picture of the potential consequences of inaction.
It does, and it emphasizes the importance of continued research monitoring and international collaboration to address this global challenge.
We often hear about the impact of climate change on glaciers, but this deep dive has given me a much deeper appreciation for the complexity of these systems.
Yeah, I agree. It's easy to oversimplify. But the reality is that these are incredibly dynamic and nuanced environments. It's like peeling back layers of an onion. The more we learn, the more we realize how much more there is to discover.
So where do we go from here? What are the next steps in understanding and protecting these glaciers?
Well, there are many avenues for further research. For example, studying the unique characteristics of each glacier and how those influence its response to environmental changes is key. We also need to investigate how variations in bedrock geology and topography affect the friction and slip length of the glacier.
So there's still a lot we don't know.
Definitely. And that's why continued research and monitoring are so crucial. It's about filling in the gaps in our knowledge so we can develop effective strategies for mitigating the impacts of climate change.
This conversation has really opened my eyes to the intricate workings of these glaciers and their significance in the face of a changing climate.
I'm glad to hear that. And remember, it's not just about understanding these glaciers for their own sake. It's about understanding how their behavior affects the entire planet and ultimately all of us.
So what can listeners do to help protect these glaciers and mitigate the impacts of climate change? It often feels like an overwhelming problem with no easy solutions.
You're right. It can feel daunting. But there are steps we can all take to make a difference. Reducing our carbon footprint, supporting policies that promote renewable energy, And advocating for environmental protection are just a few examples.
It's about recognizing our interconnectedness with the natural world and understanding that even small actions can have a ripple effect.
Precisely. We are all part of this intricate web of life, and the choices we make today will shape the future of our planet, including the fate of these magnificent Tidewater glaciers.
Well said. I think that's a great note to end on. This deep dive has been incredibly insightful, and I hope it's inspired our listeners to learn more and take action. Any final thoughts?
Just a reminder that knowledge is power. The more we understand about these complex systems, the better equipped we are to make informed decisions and protect our planet for generations to come.
I could agree more. Thank you for sharing your expertise with us today.
It's been my pleasure.
You know, it's amazing to think that these glaciers, these colossal rivers of ice, are so sensitive to even subtle shifts in their environment. It really underscores the interconnectedness of everything on our planet.
It does. And one of the things this research explores is how those subtle shifts can manifest in really dramatic ways, like the actual shape of the glacier influencing its stability.
Oh, that's interesting. I remember we talked about notches and slopes, but I didn't realize the overall shape of the glacier played such a significant role. Can you elaborate on that?
Absolutely. The researchers found that the glacier's surface profile, essentially its silhouette, is a key factor in determining how it responds to stress. Think about it. A glacier with a steep, uneven slope is going to have more concentrated pressure points, kind of like a tower with a weak foundation.
Okay, that makes sense. So a smoother, more gradual slope would distribute the weight more evenly, making it less prone to cracking and calving.
Exactly. It's all about balance and distribution of forces. A more gradual slope means less stress is concentrated at the terminus, the part of the glacier that meets the ocean, which reduces the risk of those dramatic breakoffs.
It's incredible how these seemingly small details about a glacier's shape can have such a big impact on its stability.
It is. And it highlights the importance of understanding these nuances. When we try to predict the future of these glaciers, it's not just about how much the climate warms, but also how that warming affects the glacier's physical characteristics.
It's like every glacier has its own unique fingerprint, its own set of vulnerabilities based on its size, shape, and location.
Precisely. And this research provides us with valuable tools to analyze those vulnerabilities and make more accurate predictions about how individual glaciers might respond to climate change.
And those predictions are crucial for understanding the potential impact on sea levels, right? After all, these glaciers hold massive amounts of frozen water.
Absolutely. Tidewater glaciers are significant contributors to global sea level rise. And this research helps us quantify their contribution and anticipate how it might change as the climate warms.
This all feels a bit like a delicate balancing act, trying to understand this intricate dance between the glacier's shape, the forces acting upon it, and the looming threat of climate change.
It is a delicate balance, and this research emphasizes the need for continued study and monitoring. To understand these complex systems, the more we learn, the better equipped we are to make informed decisions about protecting our planet and mitigating the impacts of climate change.
It's a reminder that these glaciers are not just stunning landscapes. They are vital components of our planet's intricate ecosystem, and their fate is intertwined with our own.
Precisely. Their health is a barometer for the health of our planet, and this research underscores the urgency of addressing climate change and protecting these icy sentinels.
This deep dive has been an incredible journey into the world of Tidewater glaciers, unveiling their beauty, their complexity, and their significance in the face of a changing climate. It's been a privilege to explore this research with you. Any final thoughts before we wrap up?
I think this research beautifully illustrates the power of scientific inquiry to uncover the hidden connections in our natural world. And it serves as a call to action, urging us to delve deeper, understand more, and work together to preserve these magnificent icy giants for future generations.
Well said. And to our listeners, thank you for joining us on this deep dive. We hope it sparked your curiosity and inspired you to continue exploring the fascinating world of science and discovery. Until next time, keep diving deep.